In this work, we introduce soft shadow diffusion, a physics-inspired learning approach for 3D computational periscopy. Given a non-line-of-sight scenario where the only visible surface to the camera is the white wall, we capture the wall with the camera. We then use a novel soft shadow diffusion model to reconstruct the point cloud of the occluding component in the hidden area. We now predict the mesh using a sign distance field model. Finally, using a physics-based optimization algorithm and a total variation regularization, we combine the 3D mesh and 2D soft shadow photograph to reconstruct the 2D image of the non-occluding component in the hidden area. Now, let us see the theoretical formulation and principle behind this work. In a conventional camera system, we measure the direct reflectance property of a scene in order to image that scene. However, if the scene is blocked by a wall, for example, it is impossible for conventional camera to image the hidden scene of interest. Non-line-of-sight imaging, or computational periscopy, aims to enable the imaging of this hidden scene without direct line of sight to the camera. Here, from a photograph of the visible wall, we reconstruct the hidden scene of interest. Non-line-of-sight imaging has many potential applications, such as autonomous navigation, emergency situation, or in search and rescue operations. We will now discuss the soft shadow diffusion model in detail. Our method and approach exploits information contained in shadows. We decompose the hidden area into two: the non-light occluding component and the light occluding component. The non-light occluding component are assumed to have perfect Lambertian properties, and they are only reflectors or emitters of light, while the light occluding component are only occluders of light. Given a non-line-of-sight scenario, the non-occluders are the chair and balls, while the occluder is the 3D object occluding the chair. A camera captures the soft shadow photograph on the visible wall, which is caused by occlusion of reflected light from the non-light occluders. We train a novel soft shadow diffusion model with simulated data. The model generalizes to real-world data without training with any real data. At inference, we encode the soft shadow photograph into a latent y-hat. We then pass the latent as a conditioning through a series of iterative reverse process of the diffusion model. Starting from a random initialization of Gaussian noise, the model reconstructs the 3D point cloud of the occluding component. Next, using an SDF model, we predict the sign distance field of the 3D point cloud and use the matching cube algorithm to predict the 3D mesh of the occluding components. We now perform a grid search in the hidden environment in order to estimate the correct location of the occluding object. By discretizing the environment into multiple partitions of location, we can predict the correct location of the occluder. At iteration 0, the projected measurement of the current location is farther away from the measurement. At iteration 10, the projected measurement is closer. And at iteration 20, the projected measurement is closer than the previous iteration. And at 36, the closest location is predicted. Once the correct location is estimated, we then use a physics-based optimization method to reconstruct the 2D image of the non-occluding component of the hidden scene. Soft shadow diffusion reconstruction is inspired by the physical property of this problem. But let us see the physics-based reconstruction method that inspires the soft shadow diffusion model. Like any conventional camera system with a field of view, our imaging system also has a computational field of view. Intuitively, the computational field of view is the subset of the entire hidden scene volume that can be reliably reconstructed. These are points in the hidden scene area that contribute to shadow within the field of view of the measured line-of-sight photograph. Here, the computational field of view can be computed by projecting the edges of the non-occluding plane at some assumed distance d towards the edges of the field of view on the visible imaging wall. Doing so, we uniquely define the occluding region for reconstruction. Next, we model objects in the occluding region as an anti-pinhole occluder. In a pinhole occluder, the non-occluding image is projected on the visible wall. In an anti-pinhole occluder, also known as the pin spec occluder, a negative image is projected on the visible imaging wall. Given a pin spec as a voxel and a light source at the pixel 02 on the non-occluding plane, we can visibly see the shadow or negative image of the intensity of light at the projected location on the visible wall. And as we change the light source location, the location of the shadows changes. We can now construct an entire 3D object, such as a chair, using a number of voxels. And we can see the shadow of the chair projected on the visible imaging wall. Next, we discretize the entire hidden region into a 3D occupancy grid that helps us reconstruct the 3D object in the occluding region. Using this property, we now derive the light propagation model as a separable nonlinear least square inverse problem, where the intensity of light at any pixel P on the visible imaging wall is equal to the integral over points in the hidden area. And the numerator here is the Lambertian cosine property. The denominator is the radial falloff due to distance. V occluder is the visibility model from point X to P, and f of X is the hidden scene radiosity, while B of P is the background light and noise that might be in the imaging system. By discretizing the visible plane and the hidden scene plane into an array of pixels, we arrive at a discrete forward model y equals A into theta f plus b, where y is the soft shadow photograph captured on the visible wall, theta is the unknown light occluder, and y depends non-linearly on theta, f is the unknown non-light occluder, and y depends linearly on f, while b is the background light and noise. We formulate a Tikhonov regularized inverse problem to recover the hidden scene. This problem can be solved via an alternating minimization algorithm. However, a dense 3D occupancy grid is required to represent real and dense 3D objects. This is precluded by high computational and memory demand. Moreover, by replacing f above with its closed form estimates, we obtain a new minimization problem, where theta is computed without explicitly computing f. With soft shadow diffusion, we reconstruct this 3D with a generative diffusion model without explicitly reconstructing f. By representing theta with a point cloud, we can reduce the computational demand in the purely physics-based approach. We can also reconstruct real-world 3D objects with limited computational and memory demand. Here is a comparison between physics-based method and soft shadow diffusion method. Our result shows that we can now reconstruct dense 3D mesh representation of real-world 3D objects. And we can extend that to reconstructing the 2D image of the non-light occluding object. Here is another result that reconstructs both the 3D hidden occluder as a point cloud and as a mesh, and also reconstructs the 2D image of the non-light occluder. Here is another result that reconstructs real-world 3D objects such as a table and a 2D image of the hidden non-light occluder. Finally, we provide qualitative results of reconstructions for increasing the ambient light levels in the hidden volume.